But if it's like the 50% is my thought.
Oh my gosh.
That was my immediate thought.
There's
So it's gonna be like, it's gonna load, it's gonna have to load the first one, but then it's gonna get like the second one that hit.
Right.
All right. So it is 7:30. We are going to continue caching. It's lecture 34, lecture 33. Should have watched the recording post on Monday. Right. So we have talked about what is locality, what are the two types of locality? Temporal and spatial. And then we talked about the basics of caches. We went through many different examples of direct map caches, right? We talked about how do we figure out if we have an entry in the cache or not. And then lecture 33 was talking about how are we handling cache misses? How are we handling some writes? And it got a little bit into the set associative caches, right? So today we're going to continue on the associativity parts of caches. We're going to compare 3 different caches. All of them have 4 one-word blocks. The first one is going to be direct map. The second one will be two-way set associative. And the last one will be fully associative. We're going to look at the memory address sequence of 08068. Right? So for direct map, each one of these memory addresses can only go to how many spots? One spot. Okay. Now you get that just by taking the address modulus the number of blocks in the cache. So 0 mod 4, 0, 8 mod 4, 0, 6 mod 4, 2. Here is our cache content. So the first thing we try and access is block address 0. And from our equation up here, we got that is cache index 0. Right? And cache index 0 is initially empty. So we have a miss. And we're going to fill in cache index 0 with memory at block 0. Right? Now we can see the rest of the cache is empty. These are our 4 entries. 0, 1, 2, 3. Our second entry is block address 8, 8 mod 4, again, 0. What is in the cache at index 0? Memory at 0, so our tags are different, right? The tags are different, so that means that the data that is in the cache was not the correct data. So we need to now evict it. This is the only place in the cache that these memory locations can go to. And we're going to load in the new data. Memory at block 8. So then next access, we're trying to access 0 again, right? Cache index 0. We have at cache index 0, memory at, which again, wrong tag. So evict 8, put 0 back in. Okay. Next access is 6. 6 mod 4 is 2. There's nothing there. So we have, right? And we fill it in. We access 8 again. Cache index 0. Again, mismatch. So 8 and 0 just keep fighting over cache block or cache index 0, right? So this is one of the downsides of direct math cache. Yeah,
So would that be a capacity or a conflict miss?
these are conflict miss.
So, okay.
Because in order to have a capacity miss, it means that in between seeing that same data again, I would have filled up a fully associative cache. So in between, if this was fully associative, I need to see 4 different memory addresses in between. Because then even if it was fully associative, I would have missed them. Because that's all, I would have filled the cache. But in here, I see 0, I see 1 in between, and then I see 0 again. So that's only 1 instead of 4. So this means that they're conflicting. But if I saw like in between here, 20 different memory addresses, and then I saw 0 again, that is capacity. Because it didn't matter that they're going to fight for the same place. Right?
Yeah.
So two-way sets associative. So now the way that we're going to get our cache index is we're going to take our block address and modulus the number of sets. Okay. So I now have 2 sets, right? Because I'm two-way set associative and all of these caches are the same size. So there's only 4 one-word blocks. Okay. So again, 0 mod 2, 0, 8 mod 2, 0, 6 mod 2, 0. So they're all going to be accessing the index 0. Our replacement policy is going to be least recently used. So block address of 0, cache index is 0. Cache is initially empty. So just miss and fill in the first available block with the memory. Block address 8, cache index 0. Again, well, not again, but we're going to go to our cache index, right? We check each field, are they valid? This one is valid, right? This one is not valid. And then what do we check?
If it's full,
Well,
what's the next one, I guess?
we need to see if it's there or not first, right? So the tag, right? We want to check the tag. So this one is valid, but the tag is different, right? So that means that our data is not in cache at set 0. So we have a miss, and we're going to fill the empty spots with our data. Block address 0, cache index 0, valid, valid. Does tag match?
Yes.
Tag matches, we have a hit. Okay. Block address 6, cache index 0, valid, valid. Well, valid, valid here, these two. Do either of the tags match? No. But what was most recently used? I'm at 0. We just accessed that before. So we evict mem at 8. And then mem at 8, cache index 0, valid, valid, but no tag, right? Tags don't match. And now we just replaced 8 with 0 with 6. So 6 is most recently used. So least recently used is 0. So that's what we're going to do. So we see how we increase the associativity. So we were able to get a little bit better hit rates when we have these conflicting addresses. Right? So fully associative. We have no index. Right? Because any memory location can go to any cache. So here's our cache. Block address is 0. We look at our cache is completely empty, no valid bits. So we have a miss. So now that we have a miss, we're going to fill in any of the cache locations with the data, right? Block address 8. We go to all of the cache locations. 3 of them are not valid. 1 of them is valid. Does my tag match? Nope. So I again have a miss. And I'm going to take up one of those non-valid spots, make it valid, put memory of it. Block address 0. Valid, valid. Either of the tags match. First one matches. We have a hit. And now we just have to label this as most recently used. Okay. Memory at 6. Valid, valid. Tags match. We have miss, but we have an empty cache location. So we load memory at 6 here. Block address 8. Valid, valid, valid. Tags match. So we have a hit, right? So we again increase our associativity and we saw an increase in hit rate. Okay. So increasing associativity decreases miss rates, but we have this diminishing return. Here is an example with a fixed cache size of 64 kilobytes. And we have 16 word blocks. And the application or benchmark is spec 2000. We talked about what spec is a long, long time ago. But one way set associative is just direct match, right? We have a 10.3% miss rate. Two-way, we improve by almost 2%, right? But going from two-way to four-way, 0.3%, right? And then four-way to eight-way, 0.2%. So this is our diminishing return. Okay. And then as we increase our set associativity, we have to check more things to tell us if we have a hit or not, right? Because direct map, I have basically one place to check, right? But two-way, now I have 2 places to check. Four-way, 4 places to check. So it grows and makes our hardware more complex. All right, so here is an example of what hardware or a hardware drawing looks like of a 4-way sets associative cache. So our example here is that it's a 4 kilobyte cache with 1 word blocks, and it's 4-way sets associated. So we have in each of these blocks here. So one block is how many bits? One block here, the data part.
2.
Right? 1 word. So 32 bits. Okay. And then we are, so that gives us this offset, right? The bottom 2 bits, because this is a bytes address. Right? Then how do we figure out our index? So we figure out the index because we have this 4 kilobyte cache, right?
Right, that's it. You divide by 4 bytes, right? You divide by 4 bytes to find out how many blocks there are.
Not 4 bytes, but 4.
Just 4.
That tells us how many these things we have, right? Like how big these each individual things are. So 4 kilobytes, 2 to the what? And then divide by what's our block size?
So 2 to the 5th.
So just 4 bytes, right? 4 bytes. So that gets rid of how many of our bits? 2 of our bits. And then divide by 4 four-way set associative, and that gets rid of how many more bits?
2 more.
2 more bits, right? So we started with 12 and with 8. Right? So basically you start off the same way that you do it for direct math, right? You take the total cache size, divide it by block size. That would be your direct math index bits. But then we need to divide it by 4 again, because we have these 4 different banks. And now we have 2 bits of offset, 8 bits of index, leaves us 22 bits of tag. And when we need to figure out where our data is, if our data is here, right, we take the index bits, we go to the index of all 4 of these banks, right? We check valid, 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 right? And then we check the tag with the tag of our current address. Tag, tag of address, tag, tag of address, tag, tag of address, right? And then we use this information to tell us if there was a hit, right? And this same information will tell us which one of these blocks is the correct block that I was looking for. Okay. So if I take the order of all these results, that will tell me there was a hit. And then which one of these was one tells me which data to select. Is this picture good with you guys? Right, so locating the block in a set associative cache, we just did this, right? We have tag, we have index, we have block offset. So the hardware effort for comparison increases linearly with the number of elements in the sets, right? Because if I have 2 elements in my sets, I have 2 places to check. 4, I have 4 places. So this is more time for comparing, which means a longer hit time. So replacement policies. If I have direct map, everything goes to one place, right? There's no choice to be made. If I have set associative, any position within the set is allowed, right? So which one should we choose? We're always going to prefer a non-valid entry, right? Because that means it's currently empty. Otherwise, we need to choose among the entries in the set. So one common policy is least recently used. And we choose least recently used because of what? Temporal locality, because if it was more recently used, we're more likely to access it again. So we're choosing the one that has been unused for the longest time within that set, right? So we need to have some bits in our cache to keep track of which one is the least recently used. This is very simple for two-way. Okay. Two-way, it's just one bit, right? And it's manageable for four-way. Four-way, now I need 2 bits, right? But it gets a little bit more complicated after four-way. Another thing that you can do is random. So this is very easy to implement. And if you have sufficiently high associativity, the performance is very similar. So if you have a low associativity, like 2 or 4-way, it makes sense to use least recently used. But if you're doing something beyond that, 8-way, 16-way, fully associative, random might be better. All right, so here we're going to go over some more cache examples. We're going to consider this sequence of memory references of word addresses. Our cache size is 8 words. We're using least recently used replacement. So we need to mark each reference as a hit or miss and show the final content of the cache for different cache organizations. We're going to do a direct map cache, two-way set associative to cache with a block size of 2 words, and then a fully associative cache with a block size of 1 word. All right, so here is our direct map cache. We have these word addresses. We have 1 word blocks. So we have, and what was our cache size? 8 words. Yeah, 8 words. So we have 8 different places in our cache. So that means 3 indexes. Okay. 2 to the 3 gives me 8. All right. So let's go through these. Address. This is a word address. So we had no offsets because our block is 1 to 10. Here's the binary conversion. Okay. So if my address is 22, what is my index?
1, 0.
1, 1, 0. Cache is initially empty, right? So 1, 1, 0 is 6, right? Nothing here. We have a miss. So what goes here? Memory at 22. 25. What is my index?
0, 0, 1.
0, 0, 1. Empty, right? Goes here. What is my index? Someone else.
0, 0, 0.
Anything in my cache? miss. So I fill it in. Right? Address 56. What is my index? What's the index? Yes, again, 0, 0, 0. There is something here. What's wrong? It's not match. So what do I do with this now? Bye-bye. Right? They fight over it. And memory at 56. 40. What is my index? Yeah, 0, 0, 0. There's something here. Does it have the same tag? No. So now what's here is memory at 24 again. Index is 0, 0, 0, 0. Memory at 40 is here again. Tag. What kind of miss is this? This is a conflict miss because I just saw 24, right? So I've seen it before, meaning that this is not a compulsory miss. And then I saw 1, 2 memory addresses in between. I have 8 memory locations. So if this was a fully associative cache, I would have had a hit. My index is index 4, right? Empty. Miss. 2, 0. Okay. We see how to do this. Okay. Yeah. Two-way sets associative. We still have 8 words for our cache. We have 2 words per block. We're using least recently used. So how many sets do we have? Well, first, one block is 2 words, and we have word addresses. So we now have 1 bit of offset. So we have 8 words total. And we have 2 words per block, and then 2 sets. So that means overall, we have 2 sets. Here's our cache, right? Set 0, set 1, where each one of these entries is 2 words. So 1, 2, 3, 4, 5, 6, 7, 8 words. Okay, so it's the same size as the direct map cache. All right, address 22. What is my index now? Yes, 1. Is there anything in my cache? Yes. So what goes here? Where does it go? This one or this one?
One first one. It doesn't really matter.
Doesn't really matter. So let's just put it in the first one. And what goes in here? Memory at what?
22, 23.
Yes. 22 through 23. Because we have 2 word block. Right. 25. What is my index? is my index.
0.
Set 0 has nothing in it. So there's no tag to check, right? So we have. Now here's the important question, what goes here? Memory.
Twenty-four.
24 to 25.
Because it's offset.
Twenty-four. What's my index? There's something valid here. Does the tag match? Okay, so we have 56. What's my index? There is something valid here. Does my tag match? But there's an open spot. Memory. What goes here? This was missed. 40.
0.
Index is 0. There's two things here. Do either of the tag match? So then I have miss. Which one do I replace?
45.
That one was 3 centimeters. So 40 through 40. What's my index for 24? I have two valid things. Tags do not match. Which one do I replace? 24 through 25. And again, this is a conflict miss, right? We've seen 24 before. And there was 1, 2 things in between. So we have, if we were fully associative, 8 different places that it could go to. All right, 20. Index is, again, tags don't match. Which one do I replace? Memory. 20. 21. Okay. So this is our final cash flow. Fully associative. So fully associative. I am having, again, 1-word blocks. I have 8 words. So because 1-word block, no offsets, and because I'm fully associative, no index. Here's my cache. Address 22. Hit or miss?
Miss.
What goes here?
Memory.
25. Hit or miss?
Miss.
Over here. 24. Memory 24. 6. Memory 56. 40. Miss. 24. Hit. Right here. Right? 20. So no conflict misses, right? But we still have not as great of a hit rate before because we have one word block, so we're not taking advantage of spatial locality. Right. So how to improve cache performance? Well, our performance is going to be dictated by how many memory stall cycles we have, right? And our memory stall cycles are going to be how many memory accesses we have for our entire program. What is our miss rate? The memory accesses times the miss rate gives us
Correction.
this is just total memory access. Total memory access. I have total memory accesses times miss rate. What number does this give me?
Amount of misses.
What?
The total amount of misses?
Yes, total amount of misses, right? Follow this, right? Total amount of misses, then times miss penalty. Gives me total memory stall cycles, right? Because for every single miss, I have this penalty, right? So to improve, we can decrease miss rate. We decrease miss rates, we have less total misses, right? Or we can decrease miss penalty. We can't really decrease memory access, right? That's defined by ISA. So how can we decrease miss penalty? So we have the primary cache attached to the CPU. It is very small, but it is very fast. This minimizes our hit time to have a shorter clock cycle for these fewer pipeline stages, right? But we have a small cache, so we might have a lot of misses. So to decrease this miss penalty, we're going to introduce a level 2 cache. It's larger and it's slower than the primary cache, but it is faster than going to memory. So this will reduce the penalty because if we have it in our L2 cache, our penalty is less than going to main memory. And not some high-end systems, almost everything has L3 cache these days. So here is a multi-level cache example. So this is just one level. So we have a base CPI of 1. Our clock rate is 4 gigahertz. Our global miss rate is 2%. Main memory access time is 100 nanoseconds. So that means if I need to get data from main memory, I have to wait 100 nanoseconds, which is with a 4 gigahertz clock equivalent to waiting 400 cycles. So my miss penalty, right? 100 nanoseconds divided by cycle time, 400 cycles. And then here is my equation. So we have base CPI. And then plus we have 2% miss rates times 400. That's our miss penalty. Now, we add L2 cache. Its access time is 5 nanoseconds. So if it's not an L1 cache, maybe it's an L2 cache, right? So our penalty for accessing L2 cache is only 20 cycles rather than 400. But if we don't have an L1 or L2, we still incur 400. So here is our new CPI. We take the miss rate and penalty, right? And then miss rate times penalty. 3.4. We had 9 before. So by reducing our overall penalty, like our average penalty, we have achieved a performance speed up of 2.6 times by adding this L2 cache. We see how to calculate penalty. Yes. We see how to get the increase in CPI given the miss rate penalty. Okay. All right. So just some terminology. Hit time is the time to access the level, right? Also called access time, right? Miss penalty, time to replace a block in that level to access the next one, right? And we have these different miss rates. So local miss rates is for the memory accesses to the cache. Global miss rates is for the total number of memory accesses. Right. So we have no reading for next time. We have one last lecture of new content. It's not really new content, but you should be able to do the content that we're going to talk about on Monday without needing my guidance. But that is our last lecture. There's no class Friday, right? We have Thanksgiving week. And Wednesday and Friday next week, I will be doing review for the exam, except one group will be going at the end of the day on Friday, right? We know who this group is, right? And then the week after that, which is week 15, right? Everyone else goes, right?
What's our final schedule for this class?
Our final is Monday.
What time?
7 to 9. It's all the syllabus, I think. Okay.
Yeah, 7 a.m. to 9 a.m. So it's not really the final, right? It's going to be exactly the same kind of test that we've had before. It's not fully cumulative. It's only cumulative in the sense that you need to know the prior information to understand the new information, but it's basically just exam 3. It's going to be designed for 1 hour, just like exam 1 and exam 2. But if you want the full 2 hours, you can have the full 2 hours. Okay.